Take your towels and come with us. Take your towels and come with us. Take your towels and come with us.
Welcome, y'all, at another episode of Take the Towel podcast, and today we'll talk about astrophysics. So, today with Filippo Landini, you can present yourself.
Hi everyone, I'm Filippo. I'm 27 at the moment, and I let's say at the moment I'm working as a DevOps, but I study as an astrophysics, and before that physics, and even before that in my high school era,
Yeah, school era.
I practice artistic gymnastics in the national team. And
Cool. So, yeah, he's like a star. He was on the television, yeah, in MTV when
Yeah.
Italy had MTV in the normal television, let's say, like not with any sky or the color kind of stuff.
yeah, it was like 2010.
2010, it
2012,
was
something like that.
10 and something years ago.
Yeah.
And you were a gymnast, weren't you? You were
Yeah,
like in
yeah.
national teams.
Yeah. Well, I start to practice gymnastics simply because my mother teaches artistic gymnastics in different clubs. So when I was very young, I was super crazy. I cannot stay still for more than 2 seconds. So my mother bring me to the gym with her, and from that moment I practice artistic gymnastics.
Was it painful to do it?
Actually, no, it was very fun. It was a very funny way to pass time. I met a lot of funny people, and some of them are my friends.
You're still in contact with them.
Yeah.
Eh? Some of them
So-
they got very famous.
Yeah. Some of them they kept practice gymnastics. So
Most of them,
some
like Carlotta Ferlito, she still does. Eh?
I'm not sure about that.
You don't-
Nico Bartolini, he still practice gymnastics. I think he's in his golden age.
He's huge, isn't he?
Yeah, he's working fine.
But are you like recognized as an Italian champion or like international champion, something like that?
Well, let's say I did most of the main competition when I was in my junior years.
Mm-hmm.
So let's say I don't think anyone can remember me.
No. Yeah, of course. It doesn't matter that. No. Like over the fact that if people remembers you or not. Like, are you an international champion, Italian champion?
Well, yeah. When I was young, I won like 5 or 6 in, Italian championships.
That's a lot, I think. Huh?
Yeah, well, in my category.
It was a lot.
Yeah.
How
for
did you
my-
stop? Why?
I stopped because when I was about 17 or 18, I have an injury in my back, and this injury was, let's say, prolonged for the years, and I had my back hurts for quite
Many
a while.
years,
Yeah, for a couple of years, and so since I wasn't sure what I could do in gymnastics, I decided simply to change my life, change the
Everything,
path,
basically, yes.
change everything. And so I was very interested in astronomy and astrophysics, and so I decided to just join university in physics, and then I decided to specialize in astrophysics.
Where does this passion comes from?
I don't really know, actually. It was just something that interested in me,
Mm-hmm.
and so I decided to just keep studying and learn.
A passion,
things.
let's say.
Yeah, let's say a passion. Let's say something very, very cool,
Okay.
and not that usual, I think.
Did you do cool stuff like during the physics lessons, like cool experiments, something like that?
Well, I'd say they were cool, but I'm not sure that everyone else thinks the same.
Why?
way.
What? No, say what they were.
Where, for example, we did some optical experiments to compute the speed of light in the second year of physics. Then we studied the spectrum of some gases. And in my third year, I decided to do astronomy laboratory, and I decided to compute. I don't even recall, but it was something about galaxies. We take some observational data and we analyze how the flux of data, the differences between the incoming flux at the telescope and the actual data that we register at the computer.
What's a flux?
The income, let's say the emitted light received. Basically, in physics, you describe the flux as the energy per unit of time and this.
Energy
distance.
per unit time and distance. Okay.
Yeah. So when the light comes at you,
Yes. Okay.
you receive the light.
Okay.
And you, let's say, quantify the amount of light received. Basically, it depends on the distance of the source.
Like any kind of source as like the light here or like the sunlight in this case.
Every kind of light.
Every kind of light.
Flux as the amount of light produced per unit of time when the source is at a certain distance.
Like, are you able to calculate this now? The distance of that and the flux from that light.
Usually in astronomy, you the main telescopes and the main structure, mainly in optical band, you just collect the light, collect every possible source you can get.
Okay.
And after a deeper analysis, you can say, for example, the distance, the velocity of the source, and other properties.
How does a telescope works?
Well, simply a telescope works basically as a camera.
Okay.
Well, much bigger and much powerful.
I think way more bigger than my camera here.
Well, actually, it depends of the source you intend to observe. For example, in radio and optical band, you need big sources because the light is not, let's say,
that's
powerful.
Strong, yes.
Yeah. So you have to collect as much light as possible. Let's say when you take a picture, you expose your let's say use your chip to the light, and the chip collects all the light and then translates it into an image. The same thing happens in telescopes, for example.
Okay, so also a picture, it's basically like an amount of light.
Yeah.
Of color, the light.
The longer is the exposure, the longer the light, the longer the amount of light. Yeah, let's say the higher is the amount of light you collect.
Okay. And like how much energy does it need a telescope to work in order to work?
I don't know that.
Too much energy.
No, I don't know. No. Simply, I don't know.
You just don't know. So, like, does the scientific researchers pollute in this case?
No, not at all.
It's not polluting. Like, it doesn't need a big amount of energy, no?
Well, actually, no. I don't think so. The only thing you need is just to keep your instrument pointed to your source of interest, and you can just be there collecting light. It's not that.
So also the telescope works with a light, like a solar panel, let's say.
I'm not sure where you want to go with this. Well, simply it's basically a camera. You have some chips. You have some electric components that collect light and transfer the data.
So as a camera takes the light and the result is a picture, in the case of a telescope, takes the light and the results are datas.
Well, yeah.
That's basically it.
Data that represents stars and something else. But it's basically a picture. It's like a big camera.
It doesn't take just data, but also pictures.
Well,
of the stars and planets and
let's
stuff.
say pictures are made of data. Everything is made of data if you
Yeah,
want.
of the binary number is 01010101.
Well, yeah, actually, if you want everything, even a single, a simple picture is like
Is
a
made of
collection
01,
of,
yes,
yeah,
yes,
is a,
of a
is a
binary
collection of
number.
data.
Yes, yes.
So simply, the job of an astrophysics astronomer is to analyze those data and basically study them, make assumption, make theories, and discover stuff.
First of all, like, how was the university system in the case of the physics and astrophysics in Italy, in Milano, in the northern part of Italy?
Well, let's say I don't think I can be the
Disappointed.
well, not disappointed. I enjoy the process,
Uh-huh.
but I don't think I'm the most qualified person to talk about this, simply because in my high school years I practiced gymnastics, but I was in, let's say, in a group of people which were specialized to do gymnastics. So
Okay.
I trained most of the day for like 6 hours a day, and at the end of the day we did 3 hours of school. So I'm not very
Not the best student, let's
yeah.
say. Okay,
Yeah,
okay.
In my high school years, I didn't study very much.
I mean, who
Uh,
studied at high school? Yeah, cioè, you know, me too. I was sleeping most of the time, you know. Though
Well,
I made it out somehow. I don't know how, but I made it out.
Yeah.
But it's fine. I mean, it depends on it's what you made the difference here in the university system.
Well, yeah,
University.
in my bachelor, I had to study a lot
Yeah.
to keep up and, let's say, to even understand how to study.
Like you were saying, like you were in high school,
Yeah.
and you couldn't spend, for obvious reason, most of your time to study. So how did you manage to both, not to like to go in physics and to learn how to do calculations?
Well, as I was saying before, lots and lots of hard work and hard study.
You basically hide yourself in a cave.
Yeah.
and,
For a couple of years, I just didn't met anyone besides my my university. It was difficult, but it was also lots and lots of
it was fun.
Yeah.
What about your colleagues?
What about them?
Was there a Rajesh Kutrapali?
Well, let's say I am the Rajesh of the group.
You are the Rajesh Kutrapali, eh? Rajesh Kutrapali from Big Bang Theory, the series on Netflix. But like also about that, like is the
Scientific community.
scientific community as they are described in the Big Bang Theory?
Well, let's say we have a broad spectrum of people, but there are some peculiar characters.
There are some peculiar people like that.
Yeah.
Like my brother works in
CERN.
you know my brother. He works in CERN as
Data scientist.
as data scientist. He does stuff on the laptop.
Yeah, he's a PhD student.
Yeah, he watch YouTube videos just in Switzerland, and he
Indian YouTube video.
huh?
Indian YouTube video.
He watch Indian YouTube videos, but Indian people building stuff, of course, that kind of videos that you watch at midnight. Or like 3 o'clock in the morning, and once he was here, we were watching the Big Bang Theory, and he was like, "Oh my God, they're exactly the same." You know, like going, like eating out, watching cartoons, Star Trek, Star Wars, and stuff like that, and going in comic book store, and they're like these kind of clumsy, you know, these.
Well,
they're
actually, I'm a big fan of anime myself.
There it is. Now, first of all, difference between astronomy and astrophysics. So, the difference between astronomy and astrophysics.
Well, actually, astronomy is the most observational part of astrophysics. They both do the same work, which is study the sky and the stars, planets, and etc., the universe. But the astronomer is like more an observational part of the job, which means that you have to go to a telescope and collect data and analyze them to produce usable data, usable images. And let's say astrophysics is that part of the job that analyzes the physics that you're observing. For example, my master thesis, I analyzed a globular cluster, which is a region of the sky with a extremely high density of stars.
Okay.
And in my thesis, I analyzed the dynamic of this object, trying to understand how dynamically old was this object. Because globular clusters are, like I was saying, a region with high density of stars, but they're not static, let's say. These stars interact with each other multiple times, and every interaction transfer energy from the inside region to the outside. So over the years, the global structure of these objects.
You showed me this.
Yeah.
You showed me this. Yeah.
Actually, the picture and the evolution of this object. Maybe I don't know.
Like there is this center globulation of stuff.
Yeah, it's
and
like,
and the stars going around.
Yeah, it's all made of stars. So
Uh-huh.
simply in the central region, the amount of star is way denser.
Uh-huh.
So in actual images, it's very difficult to see the actual stars, but you see like a big white blob.
Okay.
Well, more recent images can show the very inner region of these clusters. But in my study, what I did was basically trying to understand in what phase these objects were, because during the years the energy there's a transfer of energy between the inner region to the outer, so the overall structure evolves. For example, at some age you can find a globular cluster with a fixed size, and after a while, if you can study the same object, this could be way smaller or way bigger, simply because the energy is transferred and so the overall structure changes.
So, but these globular
clusters.
Globular cluster, was it real, like, or you just theorize it?
No, they're
it's a real globular
yeah.
structure. Like, can it be dangerous?
No, actually, they're very far away.
Okay, like
Globular cluster, there's like a lot of them. I think about. I have to check, but I think they was like.
You have to check on your telescope,
my
the big
thesis.
telescope at home, you know. But is it like something starting, like a point, like a dot in the universe, or is it something moving around the universe?
Well, it's still an important field of study, how this cluster forms and how is this and which is their role in the evolution of galaxies, for example. It's very interesting. I think it's a very interesting
No,
field.
like what I was asking, if it's like moving around or it's static in the universe.
Yeah, it's moving around. Well, we have very few data of these globular clusters simply because they're not very bright, so we can see, for example, only the closest clusters in our galaxies and maybe in the Magellan Cloud, but I don't think that you can observe globular cluster in other galaxies.
Magellan Cloud, it's like a nebula.
Well, no, it's like more a dwarf galaxy.
It's a galaxy.
Kinda.
It's a small galaxy.
Let's put it this way, but it's not exactly a small galaxy.
Okay. A galaxy, it's a big mass of stars and planets.
Yeah, let's say it's a collection of stars, planets, gas, and dark matter.
Okay, so as like we are like the Milky Way, which is our galaxy, no? Like in the middle of as we are like one of these tails, which is outside of the main center of the galaxy.
Yeah.
In the main center of the galaxy, which is extremely white, what's in the middle? Is it just an amount of stars?
Well, no. At the center of most galaxies, there's a supermassive black hole, which means a black hole with masses like 10 to the 1 followed by 10 zeros. More the mass of the sun.
Which is the higher, it has a higher mass rather than our sun. Okay, like 10 billion suns, let's say. Okay, so is it like our like solar system? Is it like slowly getting attracted from this black hole, which is the Milky Way?
let's say our galaxy is like a disk with like a bulge in the central region.
Yes.
It's like the main structure is like a disk with like branches.
Yes.
Like
We're
a
one
spiral.
of the we are
We're
in this one of the branches.
In one of these branches, but the central region there's like a bulge, like a bump, a small sphere.
Yeah, yeah.
And within the spheres there's a lot of globular clusters, gas, very few gas, but in the very center of the structures there a supermassive black hole.
Okay.
The supermassive black hole is the very core of a galaxy usually.
Okay.
And since you can see a galaxy more like a sink, you know, when you fill up a sink and
you take
and
off
you- the tappo.
the tappo,
Cazzillo.
the cazzillo,
The
yes.
cazzillo. You can see the water flowing in the center,
Okay.
and so does the gas and stars in our galaxy.
So one day in some billions years, like basically the solar system will just get attracted and eaten from the core of the galaxy.
There's this concept of black holes like monsters which eats everything. Well, actually, no, that's not.
Okay.
That's not how it works. Black holes are just objects, very dense, very very gravitational importance, let's say.
Mm-hmm.
Well, they're a great influence on the neighborhood, but their influence at some point stops. So
Okay.
it's true they are in the center of the galaxies, but they're not like big eating monsters
Okay.
which
Okay.
eat everything.
Also, this is stupid. Like, it's not a black hole. Like, it's not a black. It's white.
It's not a hole.
It's not a hole. But they say that per each black hole there is like an opposite part, which is the white hole.
Yeah, that's a theory.
It's just a theory, isn't it? But
I think it's theory.
does exist a white hole?
At the moment, there's not observational proof of these objects, so I don't think.
Okay, so it's just some fairy tale, some tales.
Well, let's say it's a theory.
Okay,
It's a theoretical object which is not proven yet.
do you think it's a legit theoretical object, or it's something just?
No, I don't think things like white holes exist.
You do not believe so.
No, simply because I don't think
You don't believe that.
simply because they should be this high region of the sky with a super huge amount of light, and when emitting light it would be very difficult not to see them.
Fair enough.
I don't think this object exists.
Okay.
And other things.
Though, like, how many black holes have been seen by now? Like,
To
too
be
many
I don't know.
black holes.
Well, actually, there's a misconception of seeing a black hole, because by definition you cannot see a black hole.
Okay.
You can define the black hole as the event horizon, which means the region of the sky where the light cannot escape.
reach. Okay.
Well, not cannot reach, cannot escape. So by definition you cannot see that region, simply because there's no light which allows you to see that region.
Okay, so basically you want.
The only thing you can see is the light emitted by the border of this region. For
Yeah.
example, the famous images published recently, even for Sagittarius A star, which is the black hole in the center of a galaxy, and the other one a few years ago, basically is plasma and gas,
Mhm.
which are rotating around the black hole, and while they're rotating, they're being heated,
Okay.
and the heat emits radiation, which can be seen, and that's what we saw.
So basically, you notice a black hole. You notice a black hole just once you do not see light, and that the fact that there may be light around this like border.
Well, yeah, let's say it's very difficult to
To
detect.
explain, yes.
Well, not to explain, to detect black holes, simply because by definition they cannot be seen. You can see the effect Well, how black holes affect the neighborhood. For example, you can detect deviation from a trajectory of a stars, of a group of stars usually, or you can see the emission of a specific amount of light.
Okay.
Or for example, you can see a clear distortion of object. For example, I don't know if you ever saw the image when you can see like a smiley face.
In a black hole?
No, the effect of a black hole in some region is to deform the space-time, so the light coming from behind the black holes curves accordingly to the space. So what you see from this side is the deformed source. So for example, when an object, let's say let's say this microphone is a black hole,
okay,
and I'm trying to see the camera.
Mm-hmm.
Black holes deforms the space-time around itself, and so the light coming from the camera, which in this case is a source, will go around the black hole.
Okay.
And from my point of view, I can see like a circle. Instead of a proper camera, I see the circle of a camera, which means that the light is diffused in a circle instead of representing like a proper camera.
Okay.
It look like a ring.
Is a black hole like a ring, or it's more like a ball?
Well, it's more like a ball.
Mm-hmm.
But the ring you'll see is not the actual black hole, is the source behind the black hole.
Ah, okay, now it's more clear.
For example, in the early 90s, when Einstein published his theory, it was a very important period, because if one published a theory, you have to find a way to prove that. Let's say in 1920s, during this age, there was a solar eclipse.
Okay.
And there was an actual experiment performed by Eddington, which is an astronomer, theoretical physicist, a scientist.
A scientist.
Which look at the sky, look at the sun during this eclipse, and he was able to see a star behind the sun, simply because the sun, just like a black hole, deforms the space-time around it.
Okay.
So if I have a star behind the sun, the light coming from the source is like moves around the sun and reaches my eyes.
Okay.
So I'm able to see the stars behind a source, simply because the space-time is deformed by the presence of
the presence of black hole.
This is what I was talking about. The process I was talking about, these lenses, these like circles, is called gravitational lensing.
Okay.
Simply because there's an object, important object, which deforms the space-time and deforms the path that the light takes to reach your eyes. So it's kind of look deforms things.
Okay.
It's very, very cool. Cool effect.
It's cool, eh?
Yeah.
You think that in the mind, eh? You imagine that. That's your fetish. Your kink. Ah, yeah. It's your kink. So, does a black hole... is a black hole static as well? Or does it move? Or like just appears and then disappears?
Black holes are not statics, but they're spinning.
Okay, like
They're-
a planet.
Yeah, like basically everything.
In the universe.
Planets, stars, black holes, galaxies. Basically everything is moving. And black holes move as well. They spin around their axis. And accordingly to their velocity of rotation, they deform the space-time.
Okay.
And also, they just not move around and spin around their axis, but they also move around space and time. But there's different families of black holes. There's stellar black holes, intermediate mass black holes, massive and supermassive black holes, depending on their amount of mass.
How many years did they... how could you categorize that? Like, how long did it take to the scientific
Scientific community.
Like
get there.
to categorize black holes or
Well, simply appears that black holes are the natural end of a astronomical object. For example, stars. When stars are bigger than a specific amount of mass, there's usually let's say an explosion,
mm-hmm.
which usually produces a supernova.
Okay.
And at the end of the process,
It becomes a black
everything-
hole.
well, yeah, the mass with one that once was a star collapses in a specific region simply because there does not exist a physical process which is able to support the mass of the star itself.
Okay.
So if you not have a pressure that can keep your star living stable, they just collapse on itself, and everything keep collapsing simply because does not exist everything which can contrast this collapse.
Okay.
This collapse, this contraction. So they keep contracting, press in space, the same mass in a smaller space until an event horizon forms, and you are not able to see inside simply because while the mass is collapsing, the space-time is deformed.
Mm-hmm.
So for example, let's say if you want to leave the planet,
Okay. One day I will.
yeah, maybe. If one want to leave a planet, you have to, let's say, produce a force. You have to have a velocity which is equal or bigger than the corresponding gravitational pull. Let's say if you want to run away,
Okay.
and I keep you here,
Uh-huh.
you have to overcome my force.
It was the tease. I mean.
Yeah.
Okay.
In black holes and stars happens the same thing.
They works the same way.
Yeah, basically.
So can a star like escape a black hole? No.
Well, no. Well, usually it depends if the star is within or outside his influence radius.
Like his range of attack, let's say.
Yeah, let's say.
To make it more
let's say
easier.
it's-
And
Or for
more
example,
embarrassing.
there exist binary systems
Mm-hmm.
in where you have a black hole and a star, which can simply coexist like a binary system. For example, like the solar system. Even if there's not the sun in the center, you can have a black hole in the center, or a small black hole on the outside, but they form a system, a stable system.
So
you have a radius of influence.
like
the
a black hole itself could work as a sun, let's say.
Yeah, let's say this way. You can form systems like the sun, like the Earth and Moon,
Mm-hmm.
binary system which coexist independently.
Okay.
For example, it can be a star and a black hole, a white dwarf and a black hole, a white dwarf and a neutron star,
So-
a star and a star.
Also, the moon is like pulled from the Earth. Otherwise, it wouldn't be there. The moon, basically.
Yeah,
Right?
it's an equilibrium system.
It's the same way the sun and the Earth works, right? Like we are.
Basically, yeah.
So it's the same job of a sun could be done like from a black hole. Not the same exactly job. I know that. Okay.
Yeah,
But
basically.
like now, let's say that there is a system, like the solar system, which is which at the center of this system there is a black hole. How
affects everything.
over that are the planets of this system like livable?
Well, let's say the first things that comes to my mind is just
No.
Interstellar.
Okay.
You know Interstellar?
Yeah, I
Film.
saw.
And there's a planet.
I watched.
Yeah, there's a planet nearby the black hole Gargantua, and it could exist, but the time there's a different perception of time,
Oh, yeah, of course.
because when you get closer
Mhm.
to an important gravitational source, the velocity at which time passes,
Mhm.
it's different between this object near the black hole and the rest of the universe,
No.
which is unaffected.
Okay.
But technically, it could be a possibility.
Like the time would go faster or slower than the
Slow.
24 hours?
Slower. You can remember in the film, the astronauts spent like few hours on the planet. I don't know what was planet.
Like the
Miller.
one in the sea, the one
Yeah,
full of
yeah,
the sea,
yeah.
yeah, full of water.
They spent a very
A
few
small amount
hours,
of time, yeah. There.
while on the Earth at home, it spent years and years, decades.
Mm-hmm.
And if you keep attention when the astronauts on this planet, there's a clock ticking behind scenes. You can hear a clock ticking, tum, 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 and every
yeah.
tick is a near. A kilometer near.
Ah,
That's the difference of time between.
I didn't notice that.
Yeah, well, it's
So
not
like 1
easy
year
to-
went by like a minute,
like a second,
like a second, yeah.
like yeah, something like that. I don't exactly know the math, but
No.
people does that. For
we,
example-
we don't know how people does that, but people does that. Respect. My hands on you. Like these about the life, like they could be like livable, but though we couldn't have the sun, and we do need the sun as like the vitamin.
Like a source of energy.
Mhm.
It's- Well, actually, I don't exactly know how could work, but for example, there's a classification for a planet to be livable, and depends on the amount of radiation and the chemical composition of the atmosphere of this
Mhm.
planet. So there's a lot of factors that could influence the possibility of life on such planet.
Yeah, of
But
course.
I don't know if we are alive. I think that somewhere in the universe, somehow
There is still
there's
like,
a possibility.
Yeah,
which,
yeah. Like
This happens.
yeah, that we could live. Like, and also like, do you think we will ever reach the stars?
Well, I don't think it's a possibility for our generation,
Okay.
but it could be a challenging life, a challenging project. But maybe in few generation, I hope
In a few
It is
generations.
a possibility. Well, stars, well, let's say I don't think people realize how far is a star and how inefficient we are.
Okay, how backwards we are.
Not backwards, but simply the scales the scales in the universe are enormous, are something beyond comprehension. I think
Okay.
you can quantify a distance between us and an astronomical object, such as, for example, Andromeda. We was talking about Andromeda before, but it's very, very, very far away from us.
Like.
For example, if you have to go simply to Mars,
How long does it take? 2 minutes.
maybe for the light,
Okay. Okay.
actually not even 2 minutes, longer than minutes.
Like,
For a light speed.
how do you measure light speed? It's like 1 to.
Light speed,
No.
simply the velocity of light
Mm-hmm.
in well,
I don't know. Like one light speed, how much can it be? I don't know.
well,
One year.
light speed is not a measure.
It's not a measure
You
of
can-
time.
you can define
it's a
light
measure of
speed.
distance. Isn't it?
Light speed is a thing. It's like, say, velocity.
Uh huh.
You can measure the velocity, but I don't know. It's difficult to put in this way.
I remember
You
it was
can-
not about time, but about distance.
You mean light years? Light years is the
Okay.
distance that the light percurs during 1 year.
Okay.
Well, let's say is the space percured by the light in
Mhm.
1 year. So that's the measure of space.
Okay, my bad. My
The
bad.
speed of light is like the space over time,
Space over time.
dimensionally.
This is not very much my topic, but it was something that we had to talk about also because I have a friend as such as you, and how can I not? Also, dark matter.
Yeah, we mentioned it before.
So what's dark matter?
Well, actually, it's very difficult to explain. Let's say that at the moment we're not sure what dark matter actually is,
Mm-hmm.
but as black holes we can see the effect on dark matter. For example, in galaxies, you expect that as far away from the center as the velocity decreases in a very particular way.
Okay.
So if the velocity of very far objects from the center are still much higher of what we expect, there must be some source of energy which allows this object to rotate at the specific velocity. For example, as one goes far away from a source, I don't know, let's imagine
A light source.
no, not exactly a light source, a mass. Let's imagine a galaxy. Let's imagine a galaxy, as we was talking about before, as a disk with
Okay.
a bulge in the very center. You know, if you can look an object, you can theoretically assign to this object a specific velocity. But this velocity depends on how much mass is between the center of the system and the specific object.
Okay.
For example, the Earth goes at a specific object because the amount of mass between the center, the gravitational center, and the Earth is dictated by the sun of the sun itself. So if we just pick the sun and change it with, so for example, Jupiter, and we keep the same distance between the center, the actual center of the sun, and the position of Jupiter of the Earth.
Okay.
So imagine a double system.
This is the sun.
This is the sun. This is the Earth. The Earth goes around the sun at a specific velocity, which depends on the mass
Of the sun.
So instead of taking the sun as center, you can put Jupiter,
Okay.
keeping the same distance between the center and the Earth. The Earth goes around Jupiter much slower at the same distance.
Because it's not the same mass.
Because it's not the same mass in the very center.
Okay.
So if you outscale this object, so if you think the same system could be applied, the same logic could be applied at systems like galaxies, you have the very center of a galaxy which has a small bulge, then the disk,
Okay.
and then there's the outer space,
The outer. Okay.
theoretically. So if we're within the galaxies and we want to measure something
Outside of the galaxy.
not outside of the galaxy, but let's say on the border,
Okay.
you expect that this object, the mass of this object, the velocity of this object depends on the mass of the galaxy itself. Because what we were saying before, the velocity of this object depends on the mass within
Within the galaxy.
the area. Yeah. And so the scientists actually did this job and measured that this object more or less goes at the expected velocity.
Okay.
However, when they took an object very far away from the border, where you expect to see a velocity basically independent from the mass of the galaxy, they observed a velocity much, much higher, meaning that even if we don't see any mass between the border, the actual light border of the galaxies and this object, there must be some mass, some source of mass
In the middle.
which influences the velocity of this object very far.
Okay.
So since we do not actually see with our light, with our instruments, any source of matter which could influence the velocity of this object, we decided to call it
Dark matter. Basically, so what you can't see is just called dark matter.
Yeah, like dark energy.
Fantastic.
Yeah, for example, the universe is expanding, but we don't know how. So there's some source which keep pushing and the universe around, but we don't actually know what is going on. So we decided to call it dark energy.
There is a picture of it's like a circle, and in the middle there are galaxies and stars, of how much, like, it's a picture of the whole universe. So I saw this picture now, and can the scientific community see the borders of this part of so as the universe is in continuous expansion, right?
Well, yeah.
At each second it passes, like, Earth seconds, okay? Is it right?
Yeah.
So, but can the border be seen?
Well, actually, we think that the universe does not have a border.
Oh, fair enough. Fair enough.
Fair enough.
Fair enough.
The end.
That's it. Okay.
Well, but there's a very interesting thing you can see, which is the causality border. So,
There is a border then. Allora.
but it's not a physical border. It's a physical limitation of this universe, of the physics of the universe.
Okay.
So, let's say the assumption is that the universe is continually expanding.
Okay.
So, if you emit a photon, if you emit light from a source, and this can reach you, this can be seen.
Okay.
Okay. So, there's a difficulties when you talk about this, simply because when you watch things that goes around, the far you look, the faster,
The furthest.
yeah, the further you look,
Mm-hmm.
and let's say that the farther you look in space, the farther you look in time.
Okay.
Simply because time passes between a photon is emitted and you can observe it. For example, if the speed of light is limited,
Mm-hmm.
so there's not an infinite velocity. You cannot go around, you cannot teleport, let's say, from here to there, an infinite velocity.
Okay.
So since the speed of light is limited, it occurs time from when the source emitted a photon, emitted light, and the time at which you receive this light.
Okay.
So if let's say I light a bulb, I light a light, and I move around,
Mm-hmm.
time passes between
When you start the light and
When I
when
start-
you moved.
yeah, but there's the possibility that if the source is very, very far,
Mm-hmm.
when you receive the light emitted by the source, the actual source already moved away.
Ah, okay.
So that's the reason why when we look far,
As far as
In-
you can.
well, not as far as you can, well, when you look far in space, you're looking far
In time.
because you're looking not at what the actual object is looking at the moment.
Okay.
You're looking what the object looks when he emitted the light.
When the light started.
Yeah, when the light started. So for
Okay.
example, we can possibly observe a planet which is actually forming in our eyes, but in their reference frame, in their system of reference, they're like, for example, they're
It could be formed already.
it can be formed already. There could be a civilization.
Mhm.
A civilization could be extinct. It could
Yeah,
not be in the same spot.
I read something about that, like that from some planets, if you see the planet Earth from that planet, you could see like dinosaurs. Yes,
yeah.
yes.
So that's the main reason why. So the picture you showed
I showed
before,
before.
meaning that we're looking as far as possible for our point of view.
Mm-hmm.
There's an actual problem in this.
Okay.
So the universe is expanding, right?
Mm-hmm.
So while the universe is expanding, the actual space-time is expanding, right? So while the actual space-time is expanding, also the light within the space-time is expanding, is stretching. When an object is going away from the source,
Okay.
it is called, there's a physical process going on called redshift, which means that the light turns into a redder wavelength, a more soft, let's say, more difficult to see from a human eye.
From the human eyes.
So there's a point in time
Mm-hmm.
which what we are looking at the moment will not be visible, simply because the distance, the light is stretches so much that the actual wavelength are not visible anymore.
Okay.
Will not be visible anymore. So there's an intrinsic limit in what we see, which depends on the speed of light.
basically light has a max distance. So from our point of view, we can see a limited
limited region.
Limited
let's say,
region.
let's
from
say
our point of view.
yeah, let's
For
say we are in a
another
bubble.
point of view, million light years distance. He see another
Another region of the universe.
Yeah, let's say
but
we
not
are
the-
we create
Okay.
since the speed of light is limited, since the light speed is limited, we create a bubble.
This point of the universe, which is expanding, okay?
Yeah.
So this same point, after we saw it, it can be like here instead of straight up.
Well, yeah.
Ah,
So the limit.
I'm a genius. No, I joke.
Well, the limit is simply that the maximum distance we can see it depends on the source. What I was talking about before, it is clear, right?
Yeah.
The farther
questo l'ho
we
fatto.
the farther we look in space, the farther we look in time.
Yeah.
For the same concept, there's like a bubble that we can see within the space, but the actual universe does not. It appears that there's not
No
a
borders. Yes.
but everything is at the same level. Let's see. Even if we're looking far in time, at that point, at the physical point, they're at the same level.
Yes.
So the limit is
The limit is the sky.
yeah.
The limit is the sky. So don't worry, we're clear enough about this. Let's talk about what probably the scientific, especially the astrophysics community hate about.
Oh no.
Astrology.
Astrology. I know that.
Yes. So how much does the astrophysics community hate astrology? I don't believe it. Like, I like it to hear. Like, it's
Well,
cute, you know, stuff like
It's
that.
nice to hear. It's nice to play around, but
Yeah.
we must say that it's bullshit.
Yeah. Like it is fun to kid around, to goofy around with that. I like it to hear in like.
Well, there's not scientific foundation to astrology.
Exactly, like-
That's my point.
But
Well, I think people can think whatever they want, but let's set a ground rule that what you're talking about is bullshit.
it ain't true, man. It ain't true, man. It ain't true, girl. No, like. The fact to assumptions, like the fact that I was born like on January, and like January 1st.
Your mood and your future depend on the position of Jupiter, of Venus,
Jupiter,
of Saturn.
and I have to wear this kind of rock because it gives me this energy, you know.
And
This,
also,
like you, like the technician believes in rock stuff, and the Belician it's a Rocky, Rocky Balboa.
for example, I think that the actual astrology is even wrong because there's another constellation which is not considered, which is the constellation of the Ophiuchus.
Of the Fucus,
Ophiuchus.
e cos'è?
It's a constellation.
It's a constellation.
It's a constellation which actually exists, mainly because
What does it look like?
I don't know, an Ophiuchus.
Some people they use these stuff, your astrology sign, as a parameter, you know, like as friendship or relationship.
Yeah.
So once if I ever have a woman on my own and some kids, we will have to program when exactly to make the kid to copulate in order to have that kid in that month on that day. Okay.
Well, it's just crazy.
It's
You can actually scientifically prove that there's no correlation between the position of Earth and Jupiter. Simply, even without taking in consideration the constellation, but simply because looking at interaction between Earth and Jupiter and Earth and other planets, you can not quantify the differences at gravitational pull or actual influence.
No, but also like dude or girl. I think dude it's also for girls. Why the fuck you bore yourself, you yourself and the other people? Why the heck you have to bore yourself with this more stuff to know? You know, like just leave it chill. Fuck this shit.
Non è spenta.
No, it's working. I'm saying this stuff because I want to say. So we're finished for today. Thank you very much, Phil. Thanks the
problem.
stars. Thanks the
I tried.
astrophysics community and the astrology community. And leave a comment, leave a like, share it with your friends. And we'll see you. Leave a comment if you want to, if you wish us to speak about something in peculiar, or to, if you have any comments, if you have any questions, write down or DM us on Instagram. And see you next. Ciao. See you at the stars.